So it's a pleasure to have Dr. Benedict von Harling. He's here with us for 4 weeks. He's giving a set of 8 lectures on cosmological phase transitions and gravitational waves. So he's going to start next week the last 4 lectures, I guess. And he's going to give this talk to us today. But before that, let me just say that Benedict got his PhD from University of Heidelberg, then went to work with Tony Gergeta in Australia, then with Marcos Cerone in CISA, and then with Geraldine in DESI, and now with Alex in IFAE-Barcelona. So he has been around, and he's an expert on these topics of cosmological phase transitions, but today he's going to talk about some very interesting work that he's doing, I guess, with Alex. Thank you, Benedict.
Yeah, thank you very much for this opportunity. And is there a pointer? Maybe this is stick. Or I can use my hand.
Is there a pointer or what?
It's a pointer, and you can press the slide.
The comb, not the comb?
Okay, I can also. I guess I can use my hand if there's not.
Low tag is good.
Yeah, this is okay.
It also helps if anyone has convenient
I'm
questions.
getting attacked. Myself. Okay, so yeah, thank you very much for this opportunity. So this is. Can I move this? Actually, I also need to figure out. Okay, so I will have to. There's no automatic.
There was one, but it's not there.
Okay, so I have to move around a bit, I guess. Okay, so yeah, this is based on work together with Luigi Della Rosa and Alex Pomerol, and if you're interested, it's on the archive. Already published also. This is the archive. And okay. So let me start with some motivation for this work. As I'm sure everyone has heard, the muon-G-2 experiment at Fermi-Lab has confirmed an older result from Brookhaven. And there's now the 4 sigma discrepancy in the anomalous magnetic moment of the muon compared to what you get in the standard model. So this is quantified by this parameter delta mu, which is just the difference between the experimental value for G-2 and the standard concentration between these 2 roots. 4 sigma away from 0. I should point out that kind of the size of the discrepancy depends on how you estimate the harmonic contributions to G-2 in the standard model, and so there are some lattice calculations which find a much smaller discrepancy. So actually, a few days ago, 2 more papers confirming this. So I mean, the standard model expectation is not totally settled, but in any case, for the purpose of this talk, let's just assume there is a discrepancy. And then, as you can imagine, there's a whole zoo of models that now try to explain this discrepancy by giving additional contribution to G-2. Right? And one particular example is given by a theory with 2 vector-like fermions, a singlet S, and then S double L. And with Lagrangian given this expression here. So these are vector-like, so they have they're Dirac fermions, so they have 2 wild components, S and C and L and LC. I should say LC also carries Hilbert charge, so it's really just a heavier version of the Lambda doublet and its partner. Okay, so there are mass terms. And now the singlet couples to the left-hand doublet containing the right-handed muon, and the left-handed muon like a right-handed neutrino. H still is just essentially the complex conjugate of the Higgs. Then the vector-like, heavy vector-like L, capital L couples to the right-handed muon E, and then there are also Yukawa couplings coupling the doublet and the singlet to each other. Note that there is no, in this version, there's no tree-level mu and Yukawa coupling.
So this is working, you can pass this slide.
Ah, perfect. Oh, perfect. That's much easier. Okay. So note that there's no tree-level mu and Yukawa coupling. But this is generated now with one loop by a diagram of this type. So L, let me just briefly describe what happens. The lambda double L couples to the singlet and the Higgs, then couples to the Higgs and the vector like capital L, which then couples to the Higgs and the right-handed muon. Yeah, and then this generates a Yukawa coupling for you. So now you would expect that in this theory you get a contribution to G minus 2 from essentially the same diagram, except that I now attach a photon here to the Higgs group. And now I'm restricting here to the complex component of the Higgs and here to the neutral component of the Higgs. This is what you would naively expect to be the leading contribution in this theory to G minus 2. And now it turns out, if you work this out, that this diagram vanishes exactly. So this is kind of a bit bizarre. You have like this diagram, which is non-zero, and this diagram, which vanishes exactly. And they're very similar. Another way to phrase this is that, so if you integrate out these fermions here, S and L, then you generate a dimension 6 dipole moment operator, and this contributes to G minus 2 of the muon. But in this theory, the Wilson coefficient of this dipole moment operator is 0.
Why is 0?
Well,
This is the motivation.
this is a motivation. It's actually sorry. Okay, but first, let me say why this is interesting. And this was pointed out in this paper by Kanihama and Harling. The reason why this is interesting is that you can think of it as some kind of UV-IR conspiracy. And to see this, let us take the viewpoint of a low-energy physicist. And first, let's take the viewpoint of a low-energy physicist at energy scales far below the masses of the vector fermions. Then I can integrate S and L out, and I get a dimension 8 operator that looks like this. So let's assume that our low-energy physicist knows about the existence of this operator from quantum experiments, and also knows that there is no new contribution to G minus 2. And you can imagine the Fermi-Lab deviation goes away, or there's another contribution that's explained. Okay, so now our physicist is tempted to kind of calculate G minus 2 from this operator. Right? So, okay, first of all, you can calculate by closing the Higgs group. So let me just have a whiteboard I can actually, blackboard I can actually draw it. So this operator is like this, right? So you have L, E, and then 2 Higgses here. Right, so this is the operator. Okay, so now I can close this Higgs loop, and I obtain a contribution to the Yukawa coupling of the muon from a quartically divergent process. And our low-energy physicist does the calculation and finds that this kind of matches roughly what he would expect as measured, right? So something is generated from this process, and it matches what you would expect from experiments. But now he goes, or she goes, and attaches a photon here and calculates the contribution to G minus 2, and this vanishes. Okay, so this is a bit bizarre. I mean, of course, like you cannot actually calculate anything in this theory because it's divergent processes. But still a bit bizarre that like one divergent process gives you kind of what you expect, and the other just vanishes.
Does a charge Higgs? Is that charge shaped, the dotted line, the dashed line?
Yeah, this has to be a charge mix, right? So in general, it's a doublet, but now you can restrict to the charge component. This is the charge, and then this is the neutral one.
It's not a symmetry argument. You put two photons, it also vanishes.
I believe you can also attach more photons, but I'm not totally sure. So, anyway, so okay, it's even more, a little bit more interesting if we go at intermediate energy scale. So let's assume that there's a hierarchy between the masses of the doublet and the singlet. The doublet is much heavier than the singlet. So I can go to intermediate energy scales and just integrate out the doublet. So again, let's assume our physicist at these intermediate energy scales knows about the existence of this operator, and that there's no new contribution to G-2, right, from experiments. So now she goes and again calculates the contribution to G-2 from this operator. But now the difference is, this is a fully calculable contribution now. This is not UV divergent. And it's non-zero. If you do this calculation, it's non-zero. You find a non-zero contribution from this operator. But now at the same time, the physicist knows there is no contribution, right? So the only solution to this conundrum is that there's a UV contribution in this theory already, which exactly cancels this calculable IR contribution. And this is kind of this is what people got excited about this theory. That like there's a perspective like where you have this apparent cancellation coming from very different energy scales. And of course, the hope is kind of to eventually learn something from this about the hierarchy problem. But I mean, of course, this theory is very far away from the hierarchy problem. So at the moment, it's just a toy model that we try to.
So why you call it IR?
But it's convergent, right? I think if you calculate it, I mean, it's not UV dependent. So that's what I mean. It's calculable.
Okay.
So you get a calculable contribution, you know what it is. It's non-zero. You know that from experiment it has to be zero, so there must be a V contribution which exactly cancels this contribution.
No, my question is why you call it IR?
I don't know, that's just jargon, so I mean, just calculable, I think it's.
Okay.
I'm sorry, but if MS, the energy scale is less than MS and ML, it's supposed to be zero. I'm missing.
Sorry, what is supposed to be?
You calculated two different scales. At the lower scale it gives you something non-zero, and a higher scale it gives you zero, right?
No, I'm integrating out the doublet.
Yeah, so if you go to a high enough scale, then you can integrate them both up to that, so it gives you zero.
Yeah, of course, in UV theory you know it's zero, and we will see, I mean, again, let's not get hung up on this, this is just a motivation. I mean, this is kind of why people are interested in the theory. So, in the UV, if you have the full UV theory, you of course know it's zero. And we will see that's a symmetry reason why it's zero, so their things are kind of not mysterious at all. It's just mysterious if you go at intermediate energy scales, then you have this apparent UV-IR cancellation.
So I think it's the same question. So I don't see a cancellation.
I mean, again, so you calculate G-2 from this operator, and it is non-zero. You know from your full theory that it's zero. Right?
Sorry, it's very high energy.
I mean, it doesn't matter, right? I mean, what do you mean at very high energies? I mean, it's just zero. I mean, it's just
For
like.
any value of MS and ML, it's zero?
Yeah, of course. I mean,
Well, but then I don't understand what you just said. You said an energy scale is much less than ML, but greater than MS, it's not zero. So how can it be?
so I integrate out L. So, I mean, the reason is that integrating out L also gives a UV contribution, like a matching contribution to G-2 that must exactly cancel this contribution.
But you also only notice this if you're fairly close to the cutoff of this.
Yeah, of course. I mean, this is just.
Because if you're far away from that UV completion, that effect should be really small.
Exactly. So, I mean, well, you have to know about this operator. I know you can argue. I mean, Also,
But
I think
then I don't
I- you can
understand why
argue this-
people are so excited, because then, if you're close to the cutoff of this intermediate scale theory, then of course you expect the UV to start showing up new effects, right? So you're talking about a UV IR contribution, like it's orders of magnitude apart from each other. But of course, that operator that you have on the bottom there is only really relevant once you're close to ML. And that's what generated the
yeah, sure. I mean, also, I mean, actually, like because there's mixing, these two scales can also not be too far from each other. So
okay, so
for practical reasons, it's probably not a very big surprise. I mean,
okay,
it's a purely, okay, that's not.
so you're close to the
Yeah, so, I mean, in practical terms, our physicists may not actually be so surprised.
This is not exactly my field, so you can ignore me if you want, but I'm just trying to understand what the statement is. So the statement is if your energy scales in order of MS, then it's non-zero. Is that the correct statement?
No, the statement is, again, if I go to intermediate energy scales,
Intermediate means you're at the order of MS.
I integrate out L, right? So I get this operator.
That means you're at the order of MS energy scale, right?
Well, I'm above MS, right?
Okay, it's fine. MS at order or
Below ML, above
okay,
MS.
fine. So it's non-zero at those scales, and then it becomes zero if you go to higher energy scales.
No, it's zero at all energy scales. So it is,
Decided to
because it's a matching UV contribution. So
no, zero also below MS. Zero above ML,
Identically zero.
below MS, but in the middle there's a region where it's not zero.
No. So, I mean, it's zero everywhere. So it's just, there's now two contributions in the theory. There's this contribution, and there's a matching contribution that exactly cancels the G minus 2, which comes from integrating out the L.
So you have an argument that it's zero at all energy scales.
I have zero at all energy
And
scales.
you just don't have an argument.
I mean, the point is that at low energy scales, it's kind of mysterious because you have this cancellation between the contribution coming from this operator here and the matching UV contribution.
It's a symmetry argument why it's zero?
Yeah. So let's go on. Okay, maybe I'm spending too much time on this. I will. Yeah. Okay. So. Okay, so when Nakayama and Narigai wrote their paper, they actually couldn't come up with a symmetry reason for this cancellation, so it was even a little bit more mysterious. And they explained it by the integrand being a total derivative. So the loop integrand, you could show that it is a total derivative in this theory. Then a little bit later, Nathaniel Craig and collaborators pointed out that there is in fact a symmetry that explains the cancellation in this theory. Full UV theory, but it acts in a quite complicated way. So the easiest way to see it is if you go to the mass eigenstate basis. If the Higgs takes a vacuum expectation value, and you go to the mass eigenstate basis, then you can see it's essentially an exchange symmetry, exchanging the doublet and the singlet. This causes cancellation. Yeah, and now the purpose of the seminar is to show that you can show the cancellation from a similar exchange symmetry by using amplitude methods. And so yeah, we will phrase this in terms of EFT operators. So what we show is that the Wilson coefficient of the double moment operator is 0 using amplitude methods. And then we will also use the amplitude methods to calculate Wilson coefficients that are non-zero in a very efficient way. So then we will go away a little bit from the original motivation. So let me also point out that in the theory it's in any case not G minus 2 is not 0, of course. There's higher order contributions. For example, from this diagram, which generates the dimension 8 operator. It contributes to G minus 2, but it's now suppressed by essentially Higgs graph over the mass square of the heavy leptons. And there's also true loop contributions, of course. But yeah, this is not our point here, so we will not discuss this further. Okay. So seminar. So as I mentioned, I will use amplitude methods. So I will give a brief introduction into what amplitude methods are, what amplitudes are, and useful way to write amplitudes as spin-helicity variables. So I will give a brief introduction to that. Then I will discuss how to calculate loops from amplitudes. Okay, then I will go on to calculate the Wilson coefficient of the dipole moment operator in the theory with vector-like singlet and doublet, which vanishes, we will find, of course. And then, as I said, I will apply it to a theory where this Wilson coefficient actually doesn't vanish, which is very similar. I just replaced the singlet by a charged heavy version of the right-handed muon. And then we will find, finally we will also discuss another case where this is zero, the same theory, an operator that contributes to the Higgs decay gamma gamma, the Wilson coefficient also vanishes. Okay, so let me just say what I understand on the amplitude methods. So what I understand on the amplitude methods is that instead of defining the theory with a Lagrangian in fields, I define the theory in terms of the particle content and some fundamental on-shell tree-level amplitudes, which you could call building block amplitudes. And then all other tree-level amplitudes can be constructed from these building block amplitudes by requiring consistent factorization. So an example for the building block amplitudes are like these three-point amplitudes, where I have, say, two fermions cut into a gauge boson, and I can kind of glue them, merge them to get a four-point amplitude, or I can obtain a four-point amplitude from these by requiring that if I go on the pole of this intermediate gauge boson, then the amplitude factorizes into these two factors. Right? And so by kind of requiring factorization in all different channels that I can have, I can reconstruct my four-point amplitude, for example. And in this way, I can go to higher and higher amplitudes. There are very efficient methods how to do this. Okay, so it's very useful to use so-called spin-helicity variables to write the amplitudes. So let me briefly review what spin-helicity variables are. So the basic idea is to write a momentum not as a four-vector with the Lorentz index mu, but as a matrix with two spin indices alpha and alpha dot. And then in terms of the components of the four-vector, the matrix looks like this. And I do this by dotting the vector into the sigma matrices. So now so now the determinant of this matrix is just the momentum squared. And for massless on-shell particles, this is zero, of course. And for the moment, I'm restricting to massless particles. And everything is on-shell here anyway, so okay, so that means the determinant of this matrix vanishes, which then implies there's a fundamental theory in linear algebra that tells you that if the determinant of the matrix vanishes, I can write it as the outer product of two vectors. So I can write this matrix here as the product of the vector alpha and another vector lambda alpha and lambda tilde alpha dot. And they're usually abbreviated or written in terms of like angle bracket and a square bracket. It's kind of the notation that you will see a lot in the next slides. And the spin indices are suppressed. So for real momenta, these two objects are just a complex conjugate of each other, and I can express them in terms of the components of the four vector in this way, and then you can easily check that this can reconstruct this matrix here. But it will be useful in the following to kind of continue into the complex complex direction to consider momenta which are complex. You will see in a few slides why this is useful. And then in general, these are not the complex conjugates of each other, so you can just keep them arbitrary for intermediate steps, and then in the end, of course, I always restrict to real momenta. This is useful because the little group of a given particle acts as a simple rescaling on these spin-elasticity variables. So the little group of a massless particle is ISO2. And remember, the little group is the subset of Lorentz transformations which leave momentum invariant, right? For momentum now, it's just the product of this angle and the square bracket. And it's easy to see what kind of transformation leaves it invariant. I can rescale this by, say, some complex number t. And then I have to rescale the square bracket by t inverse. And that leaves the momentum invariant. So t is a complex number for general complex momenta. For real momenta, t just becomes a phase. Like that's really what you usually have for a little group transformation, just a phase. But for complex momenta, these can be general complex numbers. Okay, so then the amplitudes are expressed in terms of contractions of spin-elastic variables. So you can either contract two angle brackets or two square brackets. So you will always have these objects. Like the amplitudes will always involve these objects, but I and j label the different momenta of the particles involved in the scattering process. And one important property to note is that if I is equal to j, so if I have the same momenta, two spin-elastic variables with the same momenta, then this vanishes. And that's simply because these are commuting numbers. But this is anti-commuting, so if this is the same, the angle I angle, which is and square I square bracket vanishes.
Sorry, but one doesn't need to write the amplitude with a spinor list. You can write in terms of quasi-momenta. Yeah.
Sorry?
If you write the amplitude in terms of quasi-momenta, what do you lose?
In terms of what?
Just standard quasi-momenta instead of
for
momenta.
No, I mean, of course you can do it. It's just a very convenient, you will see in a moment why.
Okay.
It's just a very efficient way of writing things. So it's not. You can do everything with time, right? I mean, you can do everything, and everything is four momenta, as you wish. It's just a very convenient way. I mean, okay. And one reason why it's convenient is that so there's a theorem that tells you that the S matrix or scattering amplitudes are S matrix elements, right? Transform covariantly under the group. So if you have say particles cross momenta labeled 1 to n, and their helicities are h1 to hn, then under little group transformation, the amplitude transforms like with this factor. So some rescaling factor, which can be a priori different for each particle involved, to the -2 times the helicity of the particle. And the helicity of the particles are, just to remind you, plus -1/2 for massless fermions, plus -1 for massless vectors, and plus -2 for gravitons, and 0 for scalars. Right? And for example, if you have an amplitude involving gauge posits, and the little group covariance arises from the polarization. So knowing this transformation law now turns out that this fixes many amplitudes uniquely. Just from knowing that these variables transform this way, and knowing that the amplitude has to transform like covariantly with these weights here. This fixes a lot of amplitudes you need to. In particular, it fixes all 3-point amplitudes. So you can just immediately write down all 3-point amplitudes just by knowing how they have to transform in the loop. So here's an example. So if you have kind of a process involving two Steinmal leptons coupling to Higgs, say. This is for the Steinmal now. And now you label the momenta of the two leptons with 1 and 2, and of the Higgs with 3. So you can think of this as P1, P2, P3, but I will always just write 1, 2, 3. And you can easily convince yourself that the only object that has the right transformation properties under the little group is this thing. So you take the angle bracket from momenta 1 and the angle bracket from momenta 2, and you contract them, and that gives you the amplitude. And now you can, here are two more examples. Leptons coupling to the W boson, and Higgs is coupling to the Wagner boson. It's the same thing. You can convince yourself that the little group scaling uniquely fixes these amplitudes, so you don't have to do any calculation, or much of a calculation.
So the masses of the particles are all
Exactly. So that's the next thing I want to say. Exactly. Now you can kind of wonder why you have a 3-point amplitude for on-shell particles which are massless. And this is because I'm going to complex momenta. So for real momenta, these objects vanish, which you also easily show. But if I go to the if I continue to complex momenta, then now these can be 0. So these are kind of, so I keep, in the intermediate steps, I keep the momenta complex, so that I have these 3-point amplitudes non-zero. Then I kind of merge them to get, say, 4 and 5-point higher point amplitudes, and then I can take the momenta real, and I have the real expressions. So here's the example. For example, the amplitude, the scattering amplitude of the Higgs Hadonian boson to two leptons is now given by this expression. And this essentially arises from kind of merging these amplitudes in the right way. Yeah, you have to try around a bit, but it's relatively straightforward how to get this expression.
So you're only considering like the subdual part of L for some reason?
Sorry?
You're only considering you're only considering the chiral part?
Exactly, yeah. These are all masses, right? So exactly. Well, in a few slides talk about massive particles.
But even masses, you have the left and right.
Exactly. So yeah. So I have.
You could have had the complex conjugate, right?
Hmm?
You could have had the complex conjugate of the term.
I could have complex. Sorry.
What
What happened? You already saw the whole scenario.
You wrote down a term with the angle brackets, but not with the square brackets.
Exactly. So there's also amplitudes here. So you also can have the same expression with square brackets. So this is for two helicity minus 1/2 leptons. And then there's also expression for two helicity plus 1/2, which involves the same but with square brackets. But there's none for minus 1/2 and plus 1/2. So. Okay, so far everything was massless. Later we'll also consider massive particles. And there's also spin helicity formalisms for massive particles. And we will use the one first proposed by Kanihame Wang in this paper. And the idea is, again, you write the momentum as a matrix with two spin indices, alpha, alpha dot. But now the determinant of this matrix is no longer 0, because the determinant is a mass, right? So because it's no longer 0, it's not enough to have two spin helicity variables, but you need to double them. So you need twice the amount of spin helicity variables to describe this situation. And you can kind of nicely combine, so you have two angle brackets now and two square brackets. So they come with an upper index I and j, where ij runs from 1 to 2. And it turns out that this is just an index carrying the representation under the little group SV2 of a massive particle. So there are some nice properties allowing you to calculate with these variables, but I will not go into details here. The main point for the rest of the seminar is that so whenever you see a spin-listed variable with an upper index I or j, just remember it's a massive particle, and often I will suppress this index and instead write this as a whole variable. So whenever this is a whole variable, it's a massive particle. It's just by now the usual notation in this field. Okay, so far everything was at tree level, but now of course we're interested in loop processes. So I have to say something about how to calculate loop amplitudes using amplitudes. The starting point of this is the so-called Barcelona development decomposition, which allows you to write any loop process in terms of 4 scalar master intervals by 1 to I4. With these topologies here. So I1 just has 1 internal propagator and all momenta entering on one side, and it's called a tadpole. I2 has 2 internal propagators and the momenta enter from 2 different sides. It's called the bubble, and then there's also a triangle and a box. And the statement is that I can say, like, take a process with like 100 external particles and 100 internal propagators. By rewriting the Feynman loop diagram expression, I can always boil it down to this expression. I can always write it in terms of these 4 types of master integrals, involving only up to 4 internal propagators. It's a very strong statement. And then, so kind of the whole content of the amplitude is then contained in the coefficients multiplying these master integrals that I call C1 to C4. And then the upper indices here kind of enable the different ways I can combine the momenta to obtain these topologies here. So these coefficients are rational functions of the momenta. In general, they can also be just a rational piece, a rational function of the momenta which doesn't multiply any of these master integrals. This is called the rational term. So now these coefficients can be obtained by performing what so-called generalized unitarity cuts on both sides of this Barcelona development relation. So yeah, I guess you all remember that these so-called Karkovsky cutting rules, which tell you that, say, if you have a one loop amplitude and you cut 2 internal propagators. Cutting means you put the propagators on shell. So that it factorizes into the product of 2 tree-level amplitudes. And this gives the branch cut singularity of this process in a given shell. It turns out that you can generalize this to higher cuts, which maps into other types of singularities. You can perform up to 4 cuts. So there's 3 cuts and 4 cuts. So you can put up to 4 internal propagators on shell. So let's see how this works. So if we take the process that we will later be interested in as an example, I know that I can write this in this form as a Barcelona development decomposition. And now I know that kind of both sides have to have the same types of singularities. So now performing cuts on both sides, I have I can match the coefficients of the singularities on both sides and get relations. So for a 4-cut, what I get is, so a 4-cut, there's only 4 internal propagators in this process, so I put all 4 internal propagators on shell. And then this, on this side, this process just factorizes into the product of 4 tree-level amplitudes. Very simple expression.
Sorry, can I ask a question? So gamma and H0, were they on shell? Was gamma and H0, were they on shell?
Yes, everything is on shell.
The external guys?
I mean, later, I mean, I guess for this step, it's maybe not even necessary, but because we are working this on shell amplitudes, everything will be checked. So. I will say a little bit more about the kinematics in this situation later, so, because I have to go through some kinematic limits and other things. Okay, so this side of the relation just kind of simplifies to the product for tree-level amplitudes. On the other side, what I get is, so if I want to put 4 internal propagators on shell, the tadpole one contains 1 internal propagator, so it cannot contribute. The bubble cannot contribute either, the triangle neither. The only term that can contribute are the boxes, because it's the only object that has 4 internal propagators, right? And also, a specific cut projects onto a specific term in the stem.
Sorry, I realize now I missed an important point. So we started this talk discussing G-2, which is a cubic vertex, right? And then this photon...
No, this process, I mean, so, yes, but I mean, for G-2, you just put this to its background value, right? So, I mean...
What was the physics of it? Where did this photon come from? I think I missed something.
What do you mean with photon?
So we started with a 3-point vertex.
I mean, I had in the beginning, I had the same diagram without the photon that gives a contribution to the muon Yukawa couple.
Yeah.
Okay, this was
Ah,
just
okay,
to
sorry. And now we put a photon.
with the photon now, this gives the contribution to G-2. I mean, this gives a, okay, if you integrate out the fermions, this gives a contribution, naively at least, to the dark moment operator. And then if you put the Higgs to its vacuum expectation value, from this you get a contribution to G-2. The logic here. I'm really interested in the dark moment operator now.
But then the Higgs, is it really on shell or... sorry.
I mean...
You are going to put some contact term for the Higgs there, right?
I will say that later.
It's going to put background value.
I'll go back to the point. So, I mean, for this slide, it's just one example, and you can take any other process just to show how this technique works. So we perform the cuts. Okay, the rational term also goes away. So the upshot of this is that, like performing 4 cuts, I can obtain this coefficient or one of these coefficients from the product of 4 tree-level amplitudes. So I just write the product for tree-level amplitudes, I get this coefficient. It's a very simple way. It turns out that now, in general, obtaining the other coefficients here is a little bit more complicated. So, for example, I could go now and try to perform 3 cuts. So, not put one of these. So, not put 4 particles on shell here, but only 3. Then again, this would go away, this would go away. Now, this would project to 1 term in this series. But now in general, because the boxes have 4 internal propagators, the boxes will contribute to this relation. And then in general, you have to project out the contribution from the boxes to obtain the coefficients C3 and the Pascal decomposition. There are techniques how to do this, but it will turn out that in our case, we will need this. And the same happens for C2. So if you want to reconstruct C2 with 2 cuts, then again you get contributions from the triangles and the boxes, which you also have to project out. But yeah, so in principle you can construct all these coefficients, the Pascal decomposition from performing unitarity cuts, And this way you can reconstruct the original amplitude. And the advantage is that, like on the other side of this relation, now you're working with on-shell amplitudes, which you can write down in a very efficient way as we saw on the other side. So that's okay. Let's go on, and then we'll see a bit more how this works. So okay, before I apply this now to the process that I motivated in the beginning, let me make a little bit of propaganda. Turns out that these amplitude methods have been very fruitfully employed also for other calculations in effective field theories. And just to point out a few references, a few areas. So, for example, in EFTs, it's relatively difficult to find a basis of independent operators, because often operators are related to each other by equations of motion, and you have to work quite hard to find an independent basis of operators. It took a long time, for example, for the standard dimension 6 operators to find this basis. It turns out that using amplitudes, so amplitudes, really one operator now matches to one amplitude, and it turns out that there's no such ambiguity. So you can just write down all the amplitudes with a given set of particles, and that really matches one-to-one to a linear independent basis of operators. So that's a very useful application. And then it's also very useful to calculate unbalanced dimensions of EFT operators. Simplifies the calculation a lot. And finally, there have been these cases where some unbalanced dimensions vanished, and it was long mysterious why this happens. This found a very nice explanation, again, using amplitude methods. It turns out that these are some helicity selection rules that can determine which of the unbalanced dimensions vanish. Okay, so finally, after all this introduction or review, let's go back to the process that I motivated in the beginning. So just remind you that's the process we want to calculate. And corresponding to the double moment operator, where now we write this in terms of spin indices. Okay, so this operator matches one-to-one to an amplitude, which is given by this expression here. And that's another example where the helicity scaling, the helicity transformation properties of the amplitude uniquely fix this expression. While this, together with knowing that it's a contact interaction, so there can be no moment at the denominator, uniquely fix this expression. Okay, and now the strategy is to reconstruct, performing unitarity cuts, reconstruct the coefficients in the Pascal-Novella decomposition, and then extract the term that goes like 1 over m squared, where m squared is now an abbreviation for some combination of m, l, and s. Actually, how much time do I have? Oh,
Yeah.
sorry.
Can you do it in 10 minutes?
Yeah, I mean, I think we started at 10.
We started a little late, yes.
15 minutes?
15 minutes, okay.
Yeah. I took a bit too much time in the introduction. Okay, now 15 minutes should be fine. So, okay. Let me. Okay, so now we will do some important simplification by setting the momentum of the Higgs to 0. This comes back to your question. So we'll set the momentum of the Higgs to 0. And we'll talk a little bit more about the kinematics on the next slide. So if you have questions, maybe wait until then. Okay, so, and this has an important simplification. Namely, it turns out that in this case there are no boxes in the Pascal-Novella decomposition. And the easy way to see is this: if there were boxes, then in this process I should have a non-zero forecut. So I should be able to put 4 internal propagators on shell and get something non-zero. But this is not possible for the following reason. If I cut, so if I set this momentum to 0, the momentum flowing through this line is the same, right? So if I want to put the S propagator on shell and the L propagator on shell, this is not possible if the masses are different, just kinematically. And this is what I will assume. So there's no forecut and no boxes. Next, I will use the fact that the process we are interested in is both UV and IR finite to show that there's also no tapeholes and no triangles. Okay, let me show how this works. So for the triangles, it turns out that both the triangle master integrals and the bubble, the box master integrals contain the IR divergences in general. And you can show that the IR divergences in the triangles can only be cancelled by the boxes. So since we don't have boxes, and we know that we don't have IR divergences, we can conclude that there are no triangles. Simple.
The external particles are massive or massless?
Well, the outer particles, these are massive and these are massless, right? This momentum is non-zero, so you can check that
So the H0 is massive, right?
the H0 is just, no, the H0 is also massless, but the momentum is 0, so it doesn't, it's just anyway, you can check from the Feynman diagram that this is how I found that. Okay, so it's also UV finite because it's a high dimension operator that we generate, right? So, okay, so yes. Now you can see that because I cannot cut the two massive lines here. If I'm now looking at two cuts, I cannot cut the two massive lines simultaneously. So I always have to cut one massless line and one massive line. If I cut two massless lines, I would get a bubble that depends on the momentum squared of the photon, which is 0, and you can show that this vanishes identically. So this gives me a conclusion. So I can only get non-zero bubble contributions from cutting a massless line and a massive line. So, and then the corresponding bubble integral to leading order and epsilon has this expression here. At the same time, the tadpole has this expression here. And then you can see that kind of the divergent piece and the constant pieces in both these types of integrals agree exactly. So, yeah, so given the fact that you cancel all the 1 over epsilon poles because it's UV finite, it means that you also you cancel all the constant pieces here. So the contribution from the tadpoles go away completely. And another thing you learn from this is that from the bubbles, the only contribution that you get is the one that depends on the momentum. So you need to have some kind of momentum dependence in the bubble. Okay, you can also show that the rational terms do not contribute, but I will not go into details on this. So, okay, so now we've simplified this complicated partial development decomposition to just bubble integrals and the corresponding coefficients.
H plus is not pH is pH 0, is that what you're pH?
Sorry?
You have H plus and H 0.
Yeah. This is the charge component, this is the visual component.
Right, pH equals 0, you just mean the external. Is that right?
Exactly, the external values.
And H plus you pretend it's massless? Is that right?
Yeah, it's exactly the same. Exactly, so H plus is it's a Goldstone, right? So, okay, yeah, so let me just go a bit. There are a few things about the kinematics here. So I set the momentum of this particle to 0. Now I use conventions where all momenta are incoming, so the momenta of all 3 other particles now must sum to 0, right? And then you can easily see that this means you cannot keep all 3 other particles massless anymore. So for example, if we keep the lepton doublet and the photon massless, then you can see that the momentum squared is now the momentum squared of the right-hand muon. And if you want this to be non-zero, the right integral must be massive.
Do you have any gauge dependence on the loops? Do you have any gauge dependence?
No, I mean the nice thing is that the amplitudes are gauge independent, right? So,
But when you compute the loops, they are not.
hmm?
The loops are not, because
No, I mean I'm only working. I'll show you in a second. So I'm only working with on-shell objects. So there's no. I'm never doing actually loop calculation here. Right? So
This is not a final diagram.
okay.
I mean,
Looks like one, but it's not.
it's a Feynman diagram that tells you how to kind of it separates into on-shell amplitudes after performing the
But
cuts.
everything is gauge invariant, right?
Everything is on-shell and gauge invariant. So,
Okay.
so you don't have to. That's the main. Usually considered the main nice aspect about amplitudes.
Yeah, because the statement that H plus is massless is a gauge
Yeah.
dependent statement.
Okay, anyway, so let me just to speed up a bit. So, okay, so the lesson is that I have to give a small mass to the right hand mu, and this is just like, it acts like as a regulator, so I can keep the mass on 0 at intermediate steps, and then in the end send it to 0. Okay, so as I said, we only have 2 cuts to consider, and the only 2 cuts we have to consider involve cutting one massive propagator and one massless propagator. And we also have to ensure that kind of what we cut, if we perform a cut, then I have a non-zero momentum entering on the one side, because these are the only contributions that are non-dimensional. So this leaves me with 2 types of cuts. So I can cut here, because or I can have this cut. Okay. And now the nice thing is that these 2 cuts are simply related by exchanging the masses. And the way you can see this is because this momentum is 0. These propagators here, if you think about a Feynman diagram, I can just freely interchange them because the same momentum flowing here, so I can just move it around and like get the same topology as cut S for cut L by exchanging the masses. Okay, so meaning we have boiled everything down to calculating one cut, and then after this we just have to perform this exchange of the 2 masses and add the contribution from the second cut. Okay, so if you see, so let's look at this cut S. Cut S separates now the amplitude, the process into the product of this amplitude and this amplitude. So using spin-analysis variables, these are the expressions that you get. And then the bubble coefficient is obtained by multiplying these 2 amplitudes and performing integral over the Lorentz phase space. So the way you can see this is because I have 4 loop momenta, I integrate over 4 loop momenta, I have 2 constraints from the 2 cuts, so I have a 2-dimensional integral left. That's exactly the T-depth integral. Okay, in principle, we also have so we have massive internal particles which have these indices which I have to contract. So doing this, we can get this expression, which we can rewrite in this way. And the nice thing here is that I've written it in a form that has now, so one doesn't depend on the internal particles, which was momenta I denote with a prime. The other term does. But the term that does depend on the internal momenta and was D-Lewis integral would become non-trivial. You see has a contraction of the angle brackets 1, 2 in this way, but the amplitude that you're looking for has this form. You can easily convince yourself that kind of from this type of expression you can never get to this expression. It's a very straightforward way to see that this term cannot contribute. You can also perform the D-Lewis integral, and then you see that this vanishes. So we are left with this piece. And then this doesn't depend on the internal momenta, so the d-ellipse integral is trivial, it's just a normalization factor that multiplies it. Okay, so I can rewrite the coefficient in this way, and now remember that in the Barcelona decomposition I have to multiply this now by the corresponding bubble integral, and then take the limit to extract the 1/m squared piece. The bubble integral has this form, and the piece that contributes is this one, as I mentioned already. Okay, you do this, and then that's what you get. That's a contribution of this cut to the Wilson coefficient of the double moment operator. And kind of the nice thing, just to, well, okay, let me first say, so now the contribution from the other cat I just obtained by exchanging the masses. And you see that this is anti-symmetric under this exchange. So if I add the two contributions up, that vanishes. In this amplitude language, the vanishing really arises from this type of exchange symmetry under which both contributions are met.
Please go back one slide to one more. The L cut looks like it splits a 3-point function from a 5-point function. Why? Well, the S cut looks like it splits a 4 from a 4.
Yeah. So I mean, as I said, right? You can just, I mean, if you think about it, it's a corresponding family diagram. I can just interchange these propagators through the. I mean, essentially because the momentum flowing in here is 0. This propagator. Yeah, so for example, here this propagator is just a constant factor. I mean, it's just a number that I multiply with this magnitude.
This all looks so complicated. This is the simplest explanation of why this constant is 0.
I mean,
go through all this and then argue that some terms don't contribute with some square brackets.
No, okay, so if it looks complicated to you, I actually think the opposite. So let me just recapitulate what we did, right? So, I mean, the point here is that I calculate the Wilson coefficient. I didn't do actually any calculation if you go through, right? So, I went to this kinematic limit. Okay, then I have to think a little bit why only the bubbles contribute, and I only have one cut to calculate, right? But then once this is done, calculating the cut and obtaining this coefficient, and then from that the contribution to the Wilson coefficient, I didn't have to do any real calculation, right? I just multiply amplitudes. I don't even have to do the d-ellipse integral because, as I showed, the d-ellipse integral is trivial. Yeah, so I would actually argue a different way. So it's a very straightforward way, very efficient way to calculate Wilson coefficients. And if I have a few more minutes, 5? Yeah, sorry. I can quickly show you an example where this is non-zero. Okay, so that's just one thing I actually forgot to mention in the beginning. So there are two types of Yukawa couplings. Coupling the left and doublet and the singlet, and during the whole calculation I set one of them to 0. And now you can ask yourself what happens if I have the opposite situation where the other is non-zero. So I set yb to 0 and consider the case where yb prime is non-zero, and now I can consider the opposite case. Because of course it's linear and this coupling, they don't interfere. You have to consider one or the other. Okay, let me go through this very quickly. So it turns out there's a second Feynman diagram now contributing in this case that you have to calculate. So again, you have kind of two cuts for the diagram that you had before, and for the second diagram you have another type of cut. You can essentially recycle the result from the other calculation for the first type of diagram. and you get something non-zero in this case by adding the two cuts. But that's not surprising because you have the second diagram that contributes. If you add the contribution of the second diagram, you find zero. So in this case, actually, the cancellation is a little bit more complicated. It's not this nice exchange symmetry anymore, unfortunately. Okay, and finally, it's the last thing I promise I will go through quickly is the case where the Wilson coefficient is non-zero. And this happens in a theory where you, instead of having vector-like singlet and doublet, you have this vector-like charged heavy version of the red and blue of the doublet. And the Lagrangian is given by this expression. So you can, again, you have two types of Yukawa couplings, coupling the two heavy vector-like fermions. You can convince yourself that only one combination can contribute. And you have these three types of diagrams here. So now each diagram, again, you can show that there's only bubbles contributing in the Wassermann bubble decomposition as before. So you only have to calculate the two cuts. And moreover, each of these three diagrams only has one two cut to calculate. So it's a little bit simpler. The two cut of this diagram is exactly the same that we calculated the second diagram for the other process. So we can again recycle that result. And for these two diagrams, I have to calculate this two cut. But this two cut I again obtain by simple exchange between E and L. Okay, so we cycle the result from the last, from the other case for the two cut in the first diagram. Then we perform the calculation for the two cut in the second diagram. And again, it's two simple tree level amplitudes that I multiply. I can write it in a way that I see that I don't even have to perform the D-ellipse integral. So the D-ellipse integral is trivial. And from this, I can reconstruct the coefficient of Pascal development decomposition, and from this, the contribution to the Wilson coefficient of the dipole moment operator. Okay, and then kind of, so you have this contribution. You have this contribution, and I said there's another contribution that was exchanged. You have twice this contribution. You add them all up, and this is what you get. And then I think it's like you can go to the literature, as we calculated before, and it matches it. Okay. The point I want to make here is that, again, I think it's actually simpler than doing the calculation of a maybe it's a little bit more difficult at the beginning because you have to get used to all the techniques, but once you know kind of how it works, the actual calculation that you have to do is very simple. There's no loop that you do nothing.
To compute when it's not zero, I agree. But to compute when it's not zero,
exactly. So this is kind of more
to check why it's zero, I cannot believe there is not a much simpler explanation if it's symmetry.
I mean, yeah. Well, this is kind of you can, but the symmetry you see on the Lagrangian level is also quite complicated. So it's not. It's also on the Lagrangian level. It's not so simple. And the math extent basis is kind of similar. But if you do it more generally, then it is actually quite complicated. Okay, there's another case, but for this I don't have time now. You can also apply this method. There's another zero that people knew about actually, but Akani Hamed and Haragaya didn't make a big fuss about it, so it hasn't been studied so much. But you can also show that in this case, you can explain the vanishing of the Wilson coefficient in this case using our technique. Okay, so let me just summarize. So the motivation was kind of essentially how we got into this was that the DD conclusion to G minus 2 and also X gamma gamma, this is other process, vanish in certain models with vector-like fermions, and why is this the case? And I tried to convince you that applicant methods are useful to address this question. It was useful to go to this kinematic limit where the Higgs momentum is 0. then the calculation simplifies a lot using amplitude methods. And then you can understand it from this exchange symmetry, and it's also useful for cases where the Wilson distributions do not match. Thank you very much, and sorry for going over time.
We're a bit late, so if people want to leave, just leave, and people want to ask questions, just stay. So they.
Again, I'm not from this field, but you have H0 and H+. So normally when you choose a gauge, so H+ is the thing that's usually eaten by one of the vector bosons, is that right? Okay. So if you want on-shell methods, don't you have to choose if you're going to use a gauge in which the blue ones are massless, or the vector bosons are massless, or the gauge where H0 has an expectation value? I'm not sure how you can do both.
Sorry,
So you have H+, which I guess propagates if the blue ones, if the vector bosons stay massless, right?
Right.
But then you have H0, which you want to give an expectation value to,
Exactly.
which is not the gauge.
No, we don't give an expectation value, right? So we just set the momentum to 0. I mean, we just go into a certain kinematic limit, if you want to.
Very give it a constant value, not its expectation.
No, we don't give it really. I mean, the way we think about it really is just setting the momentum to 0. So
That's the same.
maybe, I don't know. I mean,
But then again,
Sure.
you could also think on that H+ as the longitudinal part of the diamond, right? That's all. We're calling it H+, but it's
I
really...
mean, you can do the same calculation. You can do the same calculation, I believe, with a W, right? So with a massive W.
The longitudinal part.
And then you have to project onto the longitudinal part, and then you should find that this is much more complicated. So in this case, yes, I'm not. Yeah. So I guess the fully gauge invariant way would be to do the calculation with a massive W, and you can also do that with amplitude methods. This is essentially the diagram that I showed at the beginning that you have to calculate. And then from there, you will find that, again, now there's a Wilson coefficient, and you can generate in principle two types of operators from this diagram, dimension 6 and dimension 8 operator, and then the dimension 6 operators can generate. We actually tried this, but it was quite complicated. So we didn't go on having this class.
Any further questions? If not, let's thanks Benedict again. Yeah, this is confusing. It's confusing. Because if you make a cut, H+ must be on shell, right?